Hi everyone, I'm Alex, head of data science at SCX and the founder at its R&D offshoot SCX Labs. About 2 months ago, we did a presentation on ACE, or Agentic Context Engineering. And today we have a V2 of this presentation, and it's a lot more special because joining me are two of the people behind the original research, Qizheng from Stanford and Shubhangi from Sambanova. Now, just to back up a bit and get an eagle eye view of this technology, ACE is a direct response to the more traditional ways to improve model performance, which are constant prompt rewriting, RAG, and fine-tuning. Why do these current approaches break all the time? Why do we see these problems show up in almost every AI rollout? That's because getting an AI model to answer one question is not the hard part. Most models can do that pretty well. The hard part is making the AI improve as the business changes. And we see that most AI agents work well on day one, but then over time start struggling as the business changes, whether it's policies or guidelines or standard practices, new products, whatever it is, a business is always changing. And you can't just keep tweaking prompts by hand or catch up with regular fine-tuning. ACE fixes that by giving each agent a living, testable, human-readable playbook, or a book of rules. So instead of retraining the model or endlessly rewriting prompts, ACE automatically modifies the context in real time. And we'll dive deeper into how ACE works, but I hope that gives you a decent idea of why we are such believers in agentic context engineering. So just a quick overview of how we'll cover this presentation. Shubhangi and Qizheng will go over the origin story of ACE and the Stanford Sambanova collaboration that made it happen, as well as the technical overview. I'll then give a practical summary of how SCX is deploying ACE and our results on benchmarks. Then Shubhangi will come back to talk about how ACE is already being deployed at various companies, and Qizheng will close with what's next on the roadmap for the technology. Now, over to Shubhangi, who will give you the story of the Stanford Sambanova collaboration.
Yeah, thanks, Alex. Hi, everyone. I'm Shubhangi from Sambanova. So here's the original story behind ACE. This whole thing started from a very pragmatic, hardware-oriented question. At Sambanova, we had built a cloud platform offering fast inference with long context support for state-of-the-art models. And we kept asking ourselves, what is a good use case that can help us showcase our strengths? What is a good agentic problem statement that will help us merge both fast inference with long context support? Around the same time, Qizheng at Stanford was working on his paper about agentic plan caching. The idea was simple. Agents generate reasoning trace, plans, and they repeat the same task from time to time. So if there is a way to cache and reuse those plans, we would not have to pay the full cost upfront. When we put those two things side by side, an intuition clicked. If we are clever enough to cache context and reuse it along with strategies, plans, and prior execution traces, we can get much of the benefit of fine tuning models to a domain purely at inference time. So, this does not involve any costly weight updates. This does not involve computational resources which are needed for expensive fine tuning. And we need little to no label training data. From a systems perspective, this became very appealing to us. We could adapt LLMs fast, cheaply, and we never had to touch the LLM weights. So that became the basis for our collaboration. Sambanova brought forward the platform, Stanford brought forward the agentic algorithms. We also took inspiration from some of the prior works, particularly Dynamic Cheat Sheet, that uses agents in an incremental fashion to build a living knowledge base. From there, our ambition grew. We did not want to limit ourselves just to agentic plans. We wanted to curate domain specific insights, code snippets, common mistakes committed by the LLMs, all in a context space called a playbook for a specific domain. We also wanted this framework to be compatible with both offline settings, which would help us optimize a system prompt, and online settings where the agent can continuously learn in production. This broader vision of agentic context curation as a lightweight substitution to expensive fine tuning is what finally crystallized into ACE. I will talk about where in the real world this sort of a framework is being used. But first, I'll hand it over to Qizheng to talk more about ACE.
Let me start with a problem that got us here, because ACE started as a research project where we want to answer the research question: can an AI agent or an AI model get better at its job without anyone touching the model's weights? A problem we call language model adaptation. The standard answer for making a model better has always been fine-tuning, collecting data, retraining the model, and redeploying the new model. But by 2025, something interesting has happened. We see that models are having much larger context windows, and inference got fast thanks to advance in hardware and in software systems. So we asked, if all the improvements lived in a context, such as instructions, knowledge, experience we see on the way, can we feed these into the model instead of into the weights? In fact, many people were already doing simple versions of this. The earliest work, Reflexion, had agents reflect on failures. JAMPA focuses on prompt optimization, which optimizes prompts from execution traces. Dynamic cheat sheet lets an agent accumulate a memory of lessons. These are real advances, but when we study them closely, we find two specific failure modes which keeps showing up. The first one we call brevity bias. Most prompt optimizers have a built-in preference for short and concise instructions. In practice, they keep throwing away exactly the stuff that matters to AI agents, like domain-specific heuristics, tricks, and experience takeaways on how to use tools, and failure modes we saw in the past. And then we would end up with a prompt that says something generic and concise, like writing good tests, while the agent actually needs very specific lessons. The second issue is worse, which we call context collapse. We ask a language model to fully rewrite its accumulated context at every step, just like what many prior work did. And we find that at some point, it compresses everything into a summary and destroys its own knowledge. We watched this happening live on one of the agent benchmarks called Aprod. If we look at the figure here in the lower right corner, at one step, the context was around 18,000 tokens, and the agent was scoring around 66 points above the naive baseline. However, one step later, it collapsed into around 100-ish tokens, a very concise summary, and accuracy consequently dropped below the non-adaptation baseline. All the accumulated knowledge was gone in a single rewrite. So the design goal here became very clear: to build a system that accumulates knowledge instead of compressing it, and that can never accidentally erase itself. Here's how ACE works. We have three different roles collaborating with one another, and the system mirrors how humans learn. The generator does the work, attempting tasks and producing reasoning traces, including mistakes, which turns out to be one of the most valuable parts. The reflector then studies these traces, like what went right, what went wrong, what was the transferable lesson here. It's the difference between doing something and learning from it. After we extract the insights, we pass these down into the curator agent, which merges these lessons into a playbook. And this is where ACE differs from everything before it. The playbook isn't a huge blob of text. It's a collection of small itemized bullets, each one containing a strategy, concept, or failure mode, with its own ID and counters tracking how often this bullet point helps or hurts. Changes arrive as small delta updates. We add a bullet point into the playbook, updating the counter. We can also merge duplicate items or remove harmful bullet points over time. The one design choice we have here, having a three-part system updating the playbook and having itemized entries instead of a huge blob of text, kill both failure modes at once. Context collapse becomes structurally impossible since nothing ever rewrites everything. And brevity bias goes away since the system is designed to grow and accumulate insights with a separate grow and refine step, instead of having things rewritten or summarized or compressed over time. So does this work in practice? On agent benchmarks like Aprod, ACE gained about 10.6% on average over strong baselines like Dynamic Cheat Sheet or Java. ACE gains around 8.6% on domain-specific benchmarks like finance. On April leaderboard, ACE running an open source model, DeepSeek 3.1, could match the top-ranked production agent powered by GPT 4.1, and actually beat it on a harder test challenge split. And most importantly, ACE does all of this without labeled data, just natural execution feedback. We also observed that ACE has much better efficiency in terms of token usage and latency in terms of adaptation than prior baselines.
Thanks, Qizheng, for that excellent deep dive. Let's just wrap it up. I'll try to summarize everything technical that you mentioned. There's one ACE analogy we always like to repeat at SCX. You don't retrain an employee every time a company policy changes. You update the documents they work from, and the employee figures it out over time. And ACE is like that for AI agents. For example, new policies come up, edge cases appear, customers ask things in unexpected ways, and internal processes shift. Normally, the way teams deal with this is expensive and messy. They either fine-tune the model, which means retraining it, or they build complicated retrieval systems, or they keep modifying and extending their prompts. And ACE gives us a cleaner option, a living playbook, which replaces the three common ways to improve models: prompt rewriting, RAG, and fine-tuning. So the ACE loop itself is simple. You give ACE a few hundred examples of what good output looks like. Then it turns those into rules. It tests those rules against a validation set. Rules that improve performance get promoted into the playbook. Rules that don't get rolled back. And failures aren't wasted. They become learning signals for the next refinement pass. So SCX took this concept of ACE and incorporated it into our platform. Then we ran some real-world benchmarks across customer service, support policy, and finance tagging. And after only a few hundred examples, we were surprised by the results. Across several benchmarks, we saw real gains without any fine-tuning. Customer service went from 45% to 53% accuracy, support policy from 50 to 65%, and finance tagging from 71 to 75%, all from playbook refinement alone. The biggest lifts come from domains full of small, specific operational rules with lots of edge and failure cases, exactly what generic models miss and fine-tuning won't capture in real time. These are rules like, if a customer reports a damaged package, ask for the order ID before promising a refund. Or if a customer asks about delivery timing, ask for the tracking number before quoting a timeline. Stuff like this needs to be consistent, and that's where ACE shines. After the initial training pass, which is just the generator agent, the one Qizheng described earlier, creating that initial raw playbook that we can start with, then comes the multiple refinement passes, and these are what makes a huge difference. So in this example, ACE started with an initial playbook that scored 30 out of 100 on a test set. So here it looks at the failures and identifies what rules the playbook is missing. For example, maybe the AI gave a generic contact support answer when it should have explained support hours, or maybe it mixed up refunds and rebates, even though those are different workflows. And these might sound like small distinctions, but they really matter in day-to-day use cases. They affect customer experience, support volume, policy compliance, and whether the AI is making promises that it really shouldn't make. So after this first refinement pass, the score improved from 30 to 40. And after the second pass, it improved from 40 to 50. This is where the cost savings become really clear. In this refinement steps, no GPUs were used, no model was fine-tuned, and no giant hand-maintained prompts were modified. Everything was done automatically. The total cost using SCX was about 28 cents AUD. So the message is, ACE can improve AI behavior at a very low operating cost compared with traditional model improvement methods. So over to Shubhangi, who will go over some real-world ACE pilots.
Thanks, Alex. So, in terms of real world traction, we've presented ACE at multiple venues, some of them being Newbank, Letta, Hippocratic AI, and SEX, among others. So, there's been a good amount of interest that we've received from both AI infrastructure companies and applied enterprise teams. The most mature production deployment so far has been by a company named AnyShift. AnyShift builds an AI SRE agent called Annie that investigates infrastructure incidents and performs root cause analysis. They put ACE into their production systems back in October 2025, even before the paper was out, specifically to solve the blank state memory problem. Every time their agent got to investigating an incident, it would repeat the same mistakes over and over again, be it looking up naming conventions or figuring out traffic patterns or figuring out which dashboards actually mattered for what service. With ACE, we've been able to curate these insights into a persistent playbook that the agent uses, which has significantly brought down the time for root cause analysis by 30%. So this has been a success use case with ACE. And they've actually written a detailed blog post about it as well. That being said, the enterprise adoption has had its own challenges. The three biggest challenges that we keep running into is first, controlling the quality of the context that goes into the playbook. We want to minimize the reflector noise and we want to actively eliminate the not so useful reflections from creeping into the playbook. The second one is that of context bloat. As the size of the playbook grows, with more and more insights being added into it, it will eventually spill over the context window for what the LLMs have been trained for. And the last is the need for custom prompt optimization at the start of the training loop, specifically the generator, curator, and the reflector prompts, which are needed to get the best results. So there is no one size fits all solution in this particular setup. These are some of the challenges with the current framework that we are working towards. I'll now hand it over to Qizheng.
So I'll talk about a few directions where ACE is heading to. The first direction that ACE is heading to is scale. ACE was originally designed around a single agent, learning from its own traces, more or less sequentially. But the world is moving towards swarms of agents with hundreds of models or agents running in parallel, which could generate an enormous number of traces. Could all of these agents learn together into shared playbooks, which will be shared knowledge condensed? It turns out that if we do this naively, dumping all the reflections from parallel agents into one prompt update, quality could degrade very badly, and the context can easily get overloaded. Our follow-up work called Combi tackles exactly this. It borrows a classic system idea of MapReduce. Agents execute and reflect in parallel, and then reflections get shuffled and hierarchically combined via parallel aggregation. And then a dynamic batch controller balances quality against delay. The result is close to optimal quality with dramatically reduced learning time, while many agents run in parallel. So the flywheel Alex described can work at fleet scale. The second direction we're looking into is continuous online learning. Today, most deployments run ACE in a loop of collection, refinement, validation, and then promotion. The next step is making that loop continuous and safe in production. We want the playbook updating live from execution feedback with the validation gate as the safety mechanism. SEX is actively working on this. Third, we're trying to build an ecosystem with playbooks as one of the centered role. Once knowledge lives in a portable, human-readable file instead of model weights, there are a lot of feasible things we can do. Playbooks can be shared between models, learn on a cheaper model, deploy on a better one. They can be composed. A shipping playbook can be composed with a response playbook plus a tone playbook, maybe eventually exchanged between different teams and organizations to achieve the easy sharing of knowledge, the way best practices are today. I'll then hand it to Alex for a summary of what we have been working.
Thanks a lot, Qizheng. And thanks everyone for joining us, for listening to the story of ACE, its origin, why it's so useful, and what it will look like in the near future. And an extra special thank you to Qizheng and Shubhangi for joining me today. Thank you both. We're really glad to be exploring ACE with such awesome, brilliant people from Stanford and Sambanova.
Thank you.
Thank you.